we have two current carrying wires, two parallel current carrying wires suspended on strings. Of course we do. Yes, you can say of course. It is going to look like this. We're going to have one suspended like this. We're going to have another suspended like this. This is going to look very familiar to a balloon problem. Note, it is not. These are infinitely long current carrying wires. We are going to know theta, plus it's supposed to be symmetric. It's not. I tried, but failed. Let's see. We're going to have theta. We're going to have h. Now, in order for this orientation to be consistent, in order for these two wires to stay like this, the two currents need to be in the same direction or opposite directions. Yeah. Opposite. Why? Because you heard it from over here? Come on, Nitish. That's four. Mr. P.
Shouldn't they be in the same direction?
Should they be in the same direction? Was the person over here incorrect? The whisper coming from one side of the room. Travis.
No, they should be in opposite directions.
Because
when they're in the same direction, they attract opposite.
they need to repel one another. In order to stay oriented like this, they need to be pushed away from one another. So let's make sure. We know we've proposed that the currents are going to be opposite directions. So let's say that one of the currents is into the board and the other current, I'm sorry, one's out and the other one's in. I got it reversed. Is in. So
It's so colorful today.
I know. I
Different markers.
don't have any black. I much prefer all black, but I can't.
This is nice. It's more like Mr. Shelby.
Okay. Well, here we go.
Oh dear,
So we have the current from the wire on the left creates a magnetic field where the wire on the right is located. Please take a moment to figure out the direction of that current. It starts with the right hand. Then the thumb points in the direction of the current. Therefore, the direction of the magnetic field at the wire on the right class is up. Up. The magnetic field from this wire and the wire on the left is going to be up at that point, right? Because it creates a magnetic field which is in this direction, so at this particular point it will be up. The magnetic force then, if we get out the same right hand for a different right hand rule, we point our fingers in the direction of class, current. We curl our fingers in the direction of the magnetic field, and the force on wire, the right wire on the right, is to the right. Gosh, should I use blue or red?
Green.
Green.
I can't use green. Using brown. The magnetic force is to the right. Let's just for yucks go through it on the other one. It should work out. The magnetic field caused on the left wire due to the current in the right wire is, class, please point, up. The current is into the page, therefore the magnetic field is going to be going clockwise around this, and therefore the magnetic field is going to be up. Therefore, the current comes out of the board, magnetic field goes up, and our thumb points to your left. Therefore, we have a magnetic force which is to the left. That is the magnetic force. Let's draw the free body diagram on just the one on the left then. We have the magnetic force which is down. Complete the free body diagram for me. Hillary?
Force of gravity going down.
And?
Tension going along the wire.
Tension going along the wire. Here is our free body diagram. Let's identify some things. Theta is equal to 3.00 degrees. H is equal to 4.50 centimeters. And lambda, the linear mass density of the wire, is 0.060 kilograms per meter. We are solving for the current, and they're both currents in the wire. They are in opposite directions, but they have the same magnitude of current, and we are solving for that current. We have drawn our free body diagram. Zach, next. Okay. We break the force of tension into its components. If this is theta here, let's use then that theta, because it's going to be the same theta. This is going to be tension, this is going to be tension in the y, tension in the x. Therefore, tension in the x direction is going to be equal to t times the sine of theta, and tension in the y direction equals t times the cosine of theta. Next, what would you like to do to Silva?
Some of the forces in the y direction.
Go ahead.
Equals F, or tension in the y direction minus force of gravity, which equals minus times the acceleration in the y, which is 0, which equals 0.
Tension in the y direction equals the force of gravity. Keep going.
Should we do x?
No, let's finish this. There's more we can do
So
with this.
t sine theta equals mg.
Generally, we don't need tension, so let's solve for tension so we can substitute it out eventually. So tension equals mass times the acceleration due to gravity divided by the sine of theta. It is cosine. Catherine, what do we do next?
Sum the forces in the x direction.
Go ahead.
So equals tension in the x direction minus magnetic force,
Keep going.
which equals mass times acceleration in the x direction equals 0.
Therefore, tension in the x direction equals the magnetic force. Keep going, Catherine.
Okay, so tension or t equals sine theta equals sine theta. Sine theta.
Magnetic force. Tim. We'll do ILB sine theta because we've already figured out the direction at this point, so we'll just do ILB sine theta. Okay. What next? Mr. B.
Everyone brought sine theta to the party.
Did they? Did they, class?
No.
Unfortunately, not the same theta. Don't worry, we'll go through what the theta is. Gary?
You want to like solve for t and then make them equal each other?
Let's just substitute at this point. I mean, we have tension equals mg cosine theta. We can substitute in. I mean, we could do it that way, but it seems more straightforward to me to just substitute in. We have mass times the acceleration due to gravity times the sine of theta over the cosine of theta equals ILB sine theta. Let's figure out these thetas because we have a bunch of them. Let's see. This cosine theta and sine theta, would you agree this theta is the same one because it's just breaking into components?
Yeah.
So we can make this tangent theta. So we have on the left mg tangent theta. On the right we have ILB. Now this angle right here is the angle, bless you, between netish what and what?
Between the current and the magnetic field.
Class, what's the angle between the current and the magnetic field? 90. Current is out, magnetic field is up, or it's in and magnetic field is up, but regardless, the sine is of 90 degrees. So we end up with mg tangent theta equals ILB. What? We don't know mass. We know theta. Current we're looking for. L we don't have. Nick.
Divide both sides by L, so M over L. That's why.
Good. We can divide both sides by L, and we can get on the left-hand side lambda times the acceleration due to gravity times the tangent of theta equals current times magnetic field. That's good. We have lambda, we have g, we have theta, we're solving for the current. We do not have B, the magnetic field, but oh look! We have to know the magnetic field at a certain distance from an infinitely long current carrying wire. Gosh, how are we going to figure that out? It's where we started the class. Today. Sierra. we have to use Ampere's law. What we are figuring out here is we need the magnetic field. Actually, let's do one more step because we're solving for the current. The current's equal to lambda times g times the tangent of theta divided by the magnetic field. We need the magnetic field. So what we have is an infinitely long current carrying wire. We're trying to figure out the magnetic field at a point. Ooh, look, I get to use red. From here, so we have the closed loop integral of what is Ampere's law. Flat.
The closed loop interval of mu naught ds.
Equals?
It's going to equal mu naught current.
Current inside what, Flat?
Inside the sphere.
Not the sphere. What's that thing called? Because it's not a sphere. It may look like one, but it's just a circle. You did, but that's okay. Michael's going to tell us what it is. Inside the Amperian loop. Okay. So we have, let's see. We've already figured out, we know the direction of the magnetic field at this point using the right-hand rule. It's going to be this direction. ds is just going to be in the same direction because it's along the tangent to the circle. So work me through Ampere's law here, please. Travis.
All right, so we got the closing integral of BDS cosine theta.
Keep going.
Theta is equal to 0, so it's just 1. B is constant, so it's pulled out. And then just closing integral is just F, which is the circumference.
Which is?
2 pi r.
2 pi, and I'm going to label it as little r, which is going to be this distance right there, just to give it a specific, is equal to mu naught times the current on the inside. The current on the inside is just the current on the wire, so B, the magnetic field, equals mu naught I divided by 2 pi r. That is the generic equation. In terms of this particular problem, we need to define r. R is going to be the distance between the two wires, something we do not actually know. So we need to figure out r. Please figure out r for me. Garrett?
Well, you can split it to like a triangle.
Sure. What are on the sides of the triangle?
Well, you have 1/2 r on the bottom, and then the hypotenuse would be h. So you do sine theta equals opposite over hypotenuse. So it'd be r over 2 over h.
Over little h and big H for the hypotenuse. So we get then r is equal to 2h sine theta. So coming back to our equation, the current was equal to, I'll just start with the main one, lambda g tangent theta divided by B, the magnetic field. We now have lambda times g times the tangent of theta divided by the quantity mu naught I over 2 pi r. So current is equal to lambda g tangent theta times 2 pi little r divided by mu naught I. And therefore, where did I get an I from? Oh, no way. Huh. Well, that's fun. We got to bring I over to the other side. It's going to make it I current squared is equal to, that's fun, lambda g tangent theta 2 pi divided by mu naught. Let's substitute in r. We have 2h sine theta. So current is equal to 4 lambda g, nope, let's put a pi there, 4 pi lambda g h sine theta tangent theta all over mu naught. And the square root of it. That's a good one. There you go. Let's plug in some numbers. 4 pi times 0.06 times 9.8 times h, which was 0.045, multiplied by the sine of 3, multiplied by the tangent of 3, all divided by mu naught, which is 4 pi times 10 to the negative 7, all taking the square root of current. Please.
Does that have to be a small angle? Because things.
I'm sorry, does it have to be the small angle?
Is this one of those times where it has to be a small angle or else it's
No, no, this is applicable no matter what the angle, because we didn't have a small angle approximation.
Okay, I got 26.9397.
Independent confirmation? Okay, great. So 20, looks like only two sig figs, 27 amps. Ah, that's a good one.
What was the question? Is it like how much current to keep them at?
Yeah, how much current to keep them in that particular orientation?